Hello there, and welcome to a gentle journey through the cosmos. Tonight, we're going to drift among the stars, exploring the most soothing secrets of the night sky. These aren't the dramatic explosions or violent collisions you might expect from space documentaries. Instead, we'll discover the quiet wonders that have been silently unfolding above us for billions of years. Peaceful phenomena that happen so slowly, so gracefully, that they seem designed to lull us into tranquility. From the gentle dance of binary stars to the slow breathing of distant galaxies, the universe holds countless stories that whisper rather than shout. Tonight, we'll explore these celestial lullabies, facts so calming they'll help ease your mind into rest. If you find these cosmic bedtime stories soothing, feel free to like this video and subscribe for more peaceful explorations. You can also share your favorite night sky memories in the comments below. But for now, let your breathing slow, your shoulders relax, and allow the gentle mysteries of space to wash over you like starlight. Let's begin our quiet voyage through the cosmos. The moon moves away from Earth by just over an inch each year. This slow, graceful retreat has been happening for billions of years, so gradually that entire civilizations have lived and died without noticing the change. Ancient astronomers who gazed up at the moon saw essentially the same celestial companion we see today, unaware that it was slowly, patiently drifting further into space. This gentle separation happens because of tidal forces, the same forces that create the rhythmic rise and fall of our oceans. As the Earth spins and the moon orbits, these invisible hands of gravity create a subtle dance that gradually pushes the moon outward. It's like a cosmic slow waltz, playing out over geological timescales that make human lifetimes feel like single heartbeats. 4 billion years ago, when life was just beginning to stir in Earth's ancient seas, the moon hung much closer to our planet. Days were shorter then, lasting only about 6 hours, and the moon appeared enormous in the sky, perhaps 3 times larger than it does now. The tides would have been spectacular, rising and falling with tremendous force across the early Earth's coastlines. But even this dramatic difference accumulated so slowly that if you could somehow travel back in time and watch the moon for a human lifetime, you'd never see it move. The change is so gradual, so patient, that it reminds us how some of the most profound transformations in the universe happen not through sudden violence, but through gentle persistence across unimaginable spans of time. Stars twinkle because of Earth's atmosphere, not because of anything happening in space itself. When starlight travels across the vast emptiness between distant suns and our planet, it moves in perfectly straight lines, steady and unwavering. But as that light enters our atmosphere, it encounters pockets of air at different temperatures and densities, like invisible hills and valleys in the sky. These atmospheric variations bend the starlight slightly, causing it to shimmer and dance as it reaches our eyes. It's the same effect you might see when looking across hot pavement on a summer day, where the air seems to ripple and waver. The atmosphere acts like a gentle, ever-changing lens, softly focusing and unfocusing the pinpricks of distant light. This twinkling happens most noticeably with stars near the horizon, where their light must pass through more atmosphere to reach us. Stars directly overhead barely twinkle at all, their light having made a shorter journey through our planet's protective envelope of air. It's a reminder that even the most distant objects in the universe are connected to us through these subtle interactions, their ancient light playing gently with our own atmosphere in an endless, peaceful dance. Astronomers sometimes call this atmospheric twinkling seeing, and on the very best nights, when the air is still and clear, the seeing is so good that stars appear to shine with steady, unwavering light. These are the nights when the universe seems to quiet down, when the cosmic shimmer settles into perfect calm. Most of the stars you can see with your naked eye are actually multiple star systems. What appears to be a single point of light is often 2, 3, or even more stars orbiting each other in graceful celestial waltzes. These binary and multiple star systems are far more common than solitary stars like our Sun. In fact, astronomers estimate that about half of all stars in our galaxy have at least one stellar companion. These stellar partnerships can last for billions of years, with stars slowly circling each other at distances that dwarf our entire solar system. Some binary pairs are so close they complete an orbit in just a few hours, while others take thousands of years to make a single revolution around their common center of gravity. They're locked in gravitational embraces that have endured since before Earth formed, dancing together through the darkness with perfect, patient rhythm. In some cases, these stellar couples are nearly identical twins, born from the same collapsing cloud of gas and dust billions of years ago. In others, the partners are dramatically different, perhaps a massive, brilliant blue star paired with a small, dim red dwarf. Yet regardless of their differences, they remain bound together by gravity's gentle but unbreakable hold, sharing their journey through space like cosmic companions on an eternal voyage. Even when we can't see both stars separately, their partnership reveals changes in their light. As itself, through subtle, one star passes in front of the other from our perspective, the combined light dims slightly, creating a regular pattern that astronomers can detect with sensitive instruments. These eclipsing binaries pulse with clockwork regularity, their light rising and falling like a slow, steady heartbeat across the cosmos. The space between stars is not completely empty. Instead, it's filled with an incredibly thin soup of gas and dust called the interstellar medium. This cosmic mist is so sparse that it makes the best vacuum we can create on Earth seem impossibly dense by comparison. In every cubic centimeter of interstellar space, you might find just 1 or 2 atoms, mostly hydrogen, floating in the vast emptiness. Yet despite its incredible thinness, this interstellar material plays a crucial role in the life cycle of stars and galaxies. It's the raw material from which new stars are born, and it's also the repository for elements forged in the hearts of dying stars. When massive stars reach the end of their lives and explode as supernovas, they scatter heavy elements like carbon, oxygen, and iron into this cosmic medium, enriching it and preparing it for the next generation of stellar birth. Over millions of years, gravity slowly gathers this diffuse material into dense clouds, regions where the interstellar medium becomes thick enough for stars to form. These stellar nurseries are places of incredible beauty, glowing softly with the light of newly born stars and painted with the colors of excited gas. The process is so gradual, so gentle, that it unfolds over timescales that make human history seem like a brief moment. Some of these interstellar clouds are dark, silhouetted against the brighter background of more distant stars. Others glow with soft reds and blues as starlight excites the gas within them, creating cosmic gardens of color that bloom silently in the depths of space. They drift through the galaxy like slow-moving weather systems, taking millions of years to cross distances that light covers in mere moments. Light pollution has hidden most of the night sky from modern eyes. In cities and suburbs around the world, artificial lighting creates a glowing dome that washes out all but the brightest celestial objects. What our ancestors saw as a river of stars stretching across the heavens, we now glimpse only as a faint smudge, if at all. The Milky Way, once so prominent that it inspired myths and legends in every human culture, has become invisible to most people on Earth. This is a recent change in human experience, happening mostly within the last century as electric lighting spread across the globe. For thousands of generations, humans lived under skies so dark and clear that the night was filled with thousands of visible stars. The Milky Way was a prominent feature of the night landscape, bright enough to cast faint shadows on moonless nights. But this cosmic hiding doesn't diminish the beauty that still exists above us. The stars are still there, still shining with the same gentle light they've carried across space for millions or billions of years. They're simply waiting patiently behind the veil of our own making, ready to reveal themselves to anyone who travels away from city lights to find truly dark skies. On clear nights far from urban areas, the full majesty of the night sky unfolds like a gentle revelation. The Milky Way emerges as a broad band of light stretching from horizon to horizon, its structure visible in delicate detail. Thousands of stars become apparent, many of them so faint they seem to hover at the very edge of vision, creating a soft background glow that connects the brighter points of light. The universe is expanding, but not in the way you might imagine. Galaxies aren't flying apart through space like fragments from an explosion. Instead, space itself is growing, gently stretching the fabric of reality and carrying distant galaxies away from us. It's as if the universe were a balloon being slowly inflated, with galaxies painted on its surface, moving apart not because they're traveling through the balloon, but because the balloon itself is expanding. This cosmic expansion was discovered less than a century ago when astronomers noticed that distant galaxies appear to be moving away from us, and the more distant they are, the faster they seem to be receding. But this apparent motion isn't movement through space in the conventional sense. It's the expansion of space itself, creating more distance between galaxies without requiring them to actually travel anywhere. The expansion is so gradual, so gentle, that it's imperceptible on any scale we can directly experience. The distance between Earth and nearby stars remains essentially constant, held together by gravity's local dominance over the cosmic expansion. Even the distance between our galaxy and its nearest neighbors changes so slowly that millions of human lifetimes would pass before the difference became noticeable. This universal stretching has been going on for nearly 14 billion years, ever since the Big Bang set the cosmos in motion, and it will likely continue forever, carrying galaxies farther and farther apart until the universe becomes a vast, dark expanse punctuated by isolated islands of stars. But that ending lies so far in the future that even the longest-lived stars will have burned out long before it arrives, making it more like a peaceful fading than a dramatic conclusion. Some stars are so stable they could shine for trillions of years, while massive stars burn through their fuel in just millions of years, living fast and dying young in spectacular supernova explosions. The smallest red dwarf stars take a completely different approach to existence. These modest stellar companions burn their nuclear fuel so slowly, so efficiently, that they could continue shining long after our sun has exhausted its energy and died. Red dwarfs are the universe's marathon runners, built for endurance rather than speed. They're smaller than our sun, cooler, and much dimmer, but what they lack in brightness they make up for in longevity. Some red dwarf stars could theoretically shine for 10 trillion years or more, a span of time so vast that it dwarfs the current age of the universe by a factor of nearly 1,000. These patient stars represent the universe's commitment to the long view. While more massive stars create the heavy elements necessary for planets and life through their dramatic deaths, red dwarfs simply persist, providing steady, reliable energy for any worlds that might orbit them. They're like cosmic lighthouses burning with quiet determination across unimaginable spans of time. In the far future, when all the massive stars have long since exploded or collapsed, when our sun has swelled into a red giant and then faded to a white dwarf, these small red stars will still be shining. They'll be the universe's final candles, burning steadily in an increasingly dark and empty cosmos. Their gentle light a reminder that sometimes the most modest things are also the most enduring. The Milky Way rotates so slowly that our entire solar system has only completed about 20 orbits since life first appeared on Earth. We're all passengers on a cosmic carousel that turns with such majestic slowness that civilizations rise and fall without noticing our movement through the galaxy. Our sun, along with its family of planets, travels at roughly 500,000 miles per hour as it circles the galactic center, yet this seemingly tremendous speed translates to one complete orbit every 225 to 250 million years. This galactic year, as astronomers call it, provides a different perspective on the passage of time. The last time our solar system was in its current position relative to the galaxy's center, dinosaurs had not yet appeared on Earth. When we complete our current orbit millions of years from now, the continents will have shifted, new mountain ranges will have risen, and evolution will have continued its patient work of reshaping life on our planet. The galaxy itself resembles a vast pinwheel with spiral arms that sweep gracefully outward from a central bulge of older stars. These arms aren't solid structures, but rather density waves, regions where stars and gas naturally congregate as they orbit. Like traffic moving through a perpetual construction zone, stars flow into the spiral arms, spend time there, and then continue on their orbits, leaving the arms behind while new stars take their place. Our solar system currently finds itself between two major spiral arms in a relatively quiet region called the local arm or Orion Spur. This cosmic suburb provides us with clear views of the galaxy's structure while keeping us safely away from the more turbulent regions where massive stars are constantly being born and dying. It's a peaceful neighborhood in an ancient city of stars where we drift quietly through space on our centuries-long journey around the galactic center. Black holes can be surprisingly gentle. Despite their fearsome reputation as cosmic monsters that devour everything in their path, most black holes spend their time in quiet solitude, barely interacting with their surroundings. The supermassive black hole at the center of our own galaxy, weighing as much as 4 million suns, sits relatively dormant, occasionally flickering with activity, but mostly just existing peacefully in the galactic core. The event horizon, that mysterious boundary beyond which nothing can escape, isn't a visible surface or wall. It's simply a point of no return defined by the black hole's immense gravity. For an outside observer, anything approaching this boundary would appear to slow down and fade away, its light stretching to longer and longer wavelengths until it becomes invisible. The process looks almost gentle from a distance, like watching something slowly dissolve into darkness. Many black holes were once massive stars that reached the end of their lives and collapsed under their own gravity. But this collapse wasn't necessarily violent or destructive to the surrounding space. The star simply compressed itself into a point of infinite density, creating a region where space and time become so distorted that our normal understanding of physics breaks down. Yet beyond the immediate vicinity of the black hole, space remains unchanged, following the same gravitational rules that govern planets orbiting stars. Some black holes have companion stars, and their relationship can persist for millions of years in a kind of cosmic dance. The black hole's gravity pulls material from its companion in a slow, steady stream, forming a glowing disk of hot gas that spirals gradually inward. This process, called accretion, can continue for eons, with the black hole growing slowly larger, while its stellar partner slowly shrinks, locked together in a gravitational embrace that spans geological time. Planets beyond our solar system drift in the darkness of space, many of them orphaned worlds without stars to call home. These rogue planets were likely ejected from their birth systems during chaotic early periods when young solar systems were still settling into stable configurations. Gravitational interactions with larger planets or passing stars sent them wandering into interstellar space, where they now travel alone through the cosmic night. Some estimates suggest there could be billions of these nomadic worlds in our galaxy, dark spheres of rock or gas floating silently between the stars. They receive no warmth from a nearby sun, no light to drive weather patterns or seasonal changes. Instead, they exist in perpetual winter, their surfaces frozen and their skies eternally black, lit only by the distant pinpricks of stars that provide no meaningful heat across the vast emptiness. Yet these lonely worlds aren't necessarily lifeless. Some rogue planets might retain enough internal heat from their formation to maintain liquid oceans beneath thick shells of ice, similar to the moons Europa and Enceladus in our own solar system. Others might have thick atmospheres that trap residual warmth, creating greenhouse effects that keep their surfaces temperate despite the absence of stellar heating. These wandering planets represent a different kind of cosmic story, one of solitude rather than community. They've traded the regular rhythms of day and night, the predictable cycles of seasons, for the ultimate freedom of interstellar travel. They're explorers of the deepest space, carrying whatever histories they accumulated during their brief time in organized solar systems out into the galaxy's quiet spaces, where they continue their journeys for billions of years without destination or purpose beyond simple existence. The cosmic web connects everything in the universe through invisible threads of dark matter. On the largest scales, galaxies aren't scattered randomly through space, but instead form a vast network of filaments and clusters, connected by bridges of invisible material. This cosmic web resembles neural networks or the intricate patterns of soap bubbles, with galaxies strung along the filaments like pearls on cosmic strings, separated by enormous voids that contain almost nothing at all. These dark matter filaments, invisible to our telescopes but detectable through their gravitational effects, act as highways for cosmic evolution. Gas flows along them toward the intersections where galaxy clusters form, providing the raw material for star formation across billions of years. The structure grows slowly, patiently, as gravity pulls matter along these invisible channels, building the architecture of the universe one galaxy at a time. The voids between filaments are among the loneliest places in existence. These cosmic deserts can be hundreds of millions of light years across, containing perhaps just a handful of galaxies in volumes that should hold thousands. A hypothetical observer in the center of such a void would see almost no galaxies in any direction, just empty darkness stretching to unimaginable distances. Yet even these empty regions play important roles in cosmic evolution. They provide space for the web to expand into, and their near-perfect emptiness makes them natural laboratories for studying dark energy, the mysterious force that drives the universe's accelerating expansion. In their vast silence, these voids hold clues to some of the deepest mysteries of cosmology, waiting patiently for future generations of astronomers to decode their secrets. Neutron stars are the universe's most precise timekeepers. These incredibly dense remnants of massive stars that have exploded as supernovae spin with such regularity that they rival the best atomic clocks humans have ever built. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles that sweep across space like lighthouse beams. When these beams point toward Earth, we detect regular pulses of radio waves that can arrive with clockwork precision. The most stable pulsars keep time so accurately that astronomers use them to detect subtle changes in space and time itself. These cosmic lighthouses have helped confirm Einstein's predictions about gravitational waves, ripples in space-time created when massive objects like black holes spiral into each other. The precision of pulsar timing is so extraordinary that changes in their pulse arrival times can reveal gravitational influences from events happening thousands of light years away. A typical neutron star packs the mass of our entire sun into a sphere only about 12 miles across, creating matter so dense that a teaspoon of it would weigh as much as a mountain. The surface gravity is so intense that the escape velocity approaches half the speed of light, and the magnetic fields can be trillions of times stronger than Earth's. Yet despite these extreme conditions, neutron stars can maintain their steady rotation for millions of years, gradually slowing down as they lose energy through their radiation. These stellar remnants represent the universe's commitment to order emerging from chaos. Born in the violence of supernova explosions, they settle into lives of remarkable stability and precision. Their steady pulses have been compared to cosmic heartbeats, marking time across the galaxy with unwavering regularity, reminding us that even in the aftermath of stellar death, nature finds ways to create beauty, order, and reliability that can persist across geological ages. Saturn's rings are younger than the dinosaurs. While Saturn itself formed over 4 billion years ago alongside the rest of our solar system, its magnificent ring system is surprisingly recent in cosmic terms. Scientists now believe these ethereal bands of ice and rock particles may have formed only a few 100 million years ago, meaning they appeared on the cosmic stage long after life had already established itself on Earth. The rings exist in a delicate balance, neither falling into Saturn nor drifting away into space. Each particle, from tiny grains smaller than sand to chunks as large as houses, follows its own precise orbit around the planet. They're held in place by a complex gravitational dance involving Saturn's moons, which act like shepherds, keeping the ring particles confined to their narrow lanes through space. What makes this system even more remarkable is its temporary nature. The rings are slowly spiraling inward, pulled by Saturn's magnetic field and atmospheric drag. In perhaps 50 to 100 million years, they will have vanished completely, leaving Saturn as a plain, ringless world like Jupiter or Neptune. Future civilizations, if any exist, will look up at Saturn and see only a pale yellow dot, never knowing that for a brief moment in cosmic history, this world wore a crown of ice that caught sunlight and scattered it into countless tiny rainbows. The material that forms the rings likely came from a moon or comet that wandered too close to Saturn and was torn apart by tidal forces. As this unfortunate visitor crossed Saturn's Roche limit, the invisible boundary where tidal forces overcome gravity, it was gently pulled apart, its material spreading into the thin, flat disk we see today. The process would have been surprisingly peaceful, more like a slow dissolution than a violent destruction. Comets are time capsules from the birth of our solar system. These dirty snowballs, as astronomers affectionately call them, have spent most of their existence in the frozen outer reaches of our solar system, preserved in a state virtually unchanged since the planets first formed. When gravitational perturbations occasionally send them falling toward the sun, they begin their spectacular transformation from dark, invisible chunks of ice and rock into the brilliant, tailed objects that have inspired wonder and sometimes fear throughout human history. As a comet approaches the inner solar system, the sun's heat begins to vaporize its surface ice, creating the glowing coma and twin tails that make these visitors so distinctive. One tail, made of dust particles, follows the comet's orbital path, while the other, composed of ionized gas, always points away from the sun, pushed by the solar wind. These tails can stretch for millions of miles, creating some of the largest objects in our solar system, yet they're so tenuous that their density is less than the best vacuum we can create on Earth. Most comets follow highly elliptical orbits that take them from the outer darkness to the inner warmth and back again over periods ranging from a few years to thousands of centuries. Halley's Comet, perhaps the most famous of these wanderers, returns every 76 years, its orbit carrying it from beyond Neptune to inside Venus's path. Each passage strips away a little more of its substance, gradually wearing it down until eventually nothing will remain but a stream of debris marking its former path through space. The Oort cloud, that vast spherical shell of cometary nuclei that surrounds our solar system, may contain trillions of these frozen time capsules, each one waiting patiently for its moment to journey sunward and briefly become a spectacular celestial display. They're reminders of our solar system's violent birth, when planets were still forming and cosmic debris filled the space between worlds, yet they've survived unchanged, carrying within their icy hearts the chemical signatures of that ancient time. Venus spins backwards compared to most planets in our solar system, rotating from east to west instead of west to east. This retrograde rotation means that if you could somehow stand on Venus's surface and survive the crushing atmosphere and extreme heat, you would see the sun rise in the west and set in the east. The planet spins so slowly that a single day on Venus, measured from sunrise to sunrise, actually lasts longer than a Venusian year. This backward rotation is likely the result of a massive collision early in the solar system's history, when a large asteroid or planet-sized object struck Venus with enough force to flip its rotation. Alternatively, gravitational interactions with the Sun and Venus's thick atmosphere might have gradually slowed and reversed its spin over billions of years. Either way, Venus now turns with patient deliberation, taking 243 Earth days to complete a single rotation while orbiting the Sun every 225 Earth days. Despite being Earth's nearest planetary neighbor and similar in size, Venus represents a dramatically different evolutionary path. Its thick carbon dioxide atmosphere creates a runaway greenhouse effect that maintains surface temperatures hot enough to melt lead, while sulfuric acid clouds shroud the planet in perpetual twilight. Yet beneath this hostile environment lies a world that might once have been more Earth-like, with possible ancient oceans that boiled away as the greenhouse effect intensified over geological time. The backwards rotation of Venus serves as a reminder that planetary evolution is far from predictable. Small changes in initial conditions or single catastrophic events can set worlds on completely different trajectories, turning potential gardens into hellish landscapes or, conversely, creating the precise conditions necessary for life to flourish. In Venus's slow, contrary spin, we see evidence of the cosmic accidents that shape planetary destinies across billions of years. The aurora borealis and aurora australis dance silently in Earth's polar skies, painting curtains of green, red, and purple light across the darkness. These ethereal displays result from the gentle collision between charged particles streaming from the Sun and Earth's protective magnetic field. When solar wind encounters our planet's magnetosphere, it creates a bow shock, like water flowing around the prow of a ship, deflecting most of the particles safely around us. But some of these charged particles find their way into our atmosphere along the magnetic field lines that converge at the poles. As they collide with oxygen and nitrogen molecules high in the atmosphere, they transfer energy that causes these gases to glow with characteristic colors. Oxygen produces the familiar green and red hues, while nitrogen contributes blues and purples to the aurora's palette. The intensity and frequency of auroral displays follow the Sun's 11-year activity cycle. During solar maximum, when our star is most active, auroras can appear at lower latitudes, sometimes visible as far south as the northern United States or as far north as southern Australia. During quieter periods, they retreat toward the poles, dancing primarily for the inhabitants of Arctic and Antarctic regions. Indigenous peoples of the far north have countless legends explaining these mysterious lights. Some cultures see them as the spirits of ancestors dancing in the sky, while others interpret them as pathways for souls traveling to the afterlife. Modern science has revealed the physical mechanisms behind auroras, but this knowledge doesn't diminish their beauty or their power to inspire wonder in anyone fortunate enough to witness their silent, flowing dance across the polar night. Time moves slightly faster at higher altitudes due to gravitational time dilation, one of the subtle effects predicted by Einstein's theory of general relativity. This isn't science fiction, it's a measurable reality that affects our daily lives in ways most people never consider. The global positioning system satellites that provide navigation for smartphones and cars must account for this time difference as their atomic clocks run faster than identical clocks on Earth's surface. The effect is incredibly small, but precisely measurable. At the altitude where GPS satellites orbit, roughly 12,000 miles above Earth, time runs about 38 microseconds faster per day than it does at sea level. This tiny difference would cause GPS coordinates to drift by several miles each day if not corrected, making the system useless for navigation. The satellites continuously adjust their clocks to stay synchronized with ground-based time, compensating for this relativistic effect. This time, dilation occurs because gravity literally warps space and time, creating what physicists call space-time curvature. The closer you are to a massive object like Earth, the stronger the gravitational field, and the slower time moves relative to regions of weaker gravity. The effect becomes more pronounced near extremely dense objects like neutron stars or black holes, where time can slow dramatically compared to distant observers. Even on Earth's surface, sensitive atomic clocks can detect tiny differences in the flow of time at different elevations. Clocks at the top of skyscrapers run slightly faster than those in basements, and clocks carried up mountains gain time compared to those left at sea level. These measurements confirm Einstein's predictions with extraordinary precision, revealing that time itself is not the universal constant we intuitively believe it to be, but rather a dimension that bends and flows like the space through which we move. The sun's core hasn't changed much in billions of years, maintaining a steady nuclear furnace that converts hydrogen into helium through fusion reactions. Deep in the solar interior, where temperatures reach 15 million degrees Celsius and pressures are billions of times greater than Earth's atmosphere, protons combine to form helium nuclei, releasing tremendous amounts of energy in the process. This energy begins a journey that will take hundreds of thousands of years to reach the sun's surface. Photons created in the core bounce randomly through the sun's dense interior, absorbed and re-emitted countless times as they gradually work their way outward. This random walk through the solar interior is so tortuous that energy created today in the core won't emerge as sunlight for several 100,000 years. The light warming your face right now began its journey during the Ice Ages, when early humans were just beginning to develop agriculture. The sun burns through approximately 4 million tons of matter every second, converting it into pure energy according to Einstein's famous equation. Yet this enormous rate of consumption represents only a tiny fraction of the sun's total mass. Our star has enough hydrogen fuel to continue its steady burning for another 5 billion years, maintaining the stable energy output that makes life on Earth possible. This stellar stability is remarkable when you consider the delicate balance required to maintain nuclear fusion. The sun's core must remain hot and dense enough to sustain fusion reactions, yet not so energetic that the reactions run away and consume the fuel too quickly. Gravity provides the compression needed for fusion, while the outward pressure of radiation prevents further collapse. This equilibrium has persisted for nearly 5 billion years and will continue for billions more, providing a steady, reliable source of energy for any life that might evolve in our solar system. Galaxies collide and merge in slow-motion cosmic ballets that unfold over hundreds of millions of years. When two galaxies encounter each other, their gravitational interaction begins long before they actually overlap, distorting their shapes and triggering waves of star formation along their spiral arms. Despite containing billions of stars each, galactic collisions rarely result in actual stellar collisions, as the vast distances between individual stars mean they simply pass by each other during the merger. Our own Milky Way is currently engaged in such a cosmic dance with the Andromeda Galaxy, our nearest large neighbor. Currently separated by about 2.5 million light-years, these two spiral galaxies are approaching each other at roughly 250,000 miles per hour. In approximately 4.5 billion years, they will begin to merge, their gravitational interaction reshaping both galaxies and likely ejecting some star systems into intergalactic space while drawing others into new orbital configurations. Computer simulations of this future collision show a surprisingly graceful process, with the two galaxies passing through each other multiple times over the course of several billion years, before finally settling into a singulars have nicknamed Milkomeda. The Sun, larger elliptical galaxy that astronomy and Earth, if they still exist at that time, will likely survive the merger unharmed, though they may find themselves in a completely different part of the combined galaxy. Such galactic mergers have been happening throughout cosmic history, gradually building larger and larger systems from smaller building blocks. The Milky Way itself shows evidence of past mergers, with streams of stars marking the remains of smaller galaxies that were consumed billions of years ago. These ancient collisions helped build the galaxy we call home today, adding their stars, gas, and dark matter to our cosmic neighborhood, in a process that continues even now as we slowly absorb nearby dwarf galaxies through our gravitational influence. The cosmic microwave background radiation bathes the entire universe in the faint afterglow of creation itself. This ancient light, stretched and cooled by nearly 14 billion years of cosmic expansion, reaches us from every direction in space, carrying information about the universe as it existed when it first became transparent to light. At that time, roughly 380,000 years after the Big Bang, the cosmos had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely through space for the first time. This primordial radiation has a nearly perfect black-body spectrum corresponding to a temperature of just 2.7 degrees above absolute zero, making it barely detectable above the background noise of radio receivers. Yet despite its faintness, this cosmic whisper contains a treasure trove of information about the early universe, including tiny temperature fluctuations that represent the seeds from which galaxies and galaxy clusters would eventually grow. The cosmic microwave background is remarkably uniform across the sky, varying by only a few parts in 100,000 from one direction to another. This extraordinary smoothness tells us that the early universe was in a state of almost perfect equilibrium, with matter and energy distributed nearly evenly throughout space. The slight variations that do exist correspond to regions that were slightly denser or less dense than average, providing the gravitational seeds around which structure would later form. When you tune an old analog television or radio to a frequency between stations, about 1% of the static you hear comes from this ancient cosmic radiation. In that gentle hiss lies the echo of creation itself, the stretched and faded light of the universe's fiery birth, still washing over us with its quiet testimony to the extraordinary events that set the cosmos in motion nearly 14 billion years ago. Many galaxies contain supermassive black holes that sleep peacefully at their centers, waiting millions of years between meals. These cosmic giants, some weighing billions of times more than our Sun, spend most of their existence in quiet dormancy, barely affecting their surroundings. Unlike the dramatic portrayals often seen in science fiction, these black holes don't actively hunt for material to consume. Instead, they wait patiently as gas and dust occasionally drift within their gravitational reach. When a supermassive black hole does feed, the process unfolds with surprising gentleness over thousands or millions of years. Material doesn't plunge directly into the black hole, but instead forms an accretion disk, spiraling slowly inward like water circling a drain. As this material gradually descends toward the event horizon, it heats up and begins to glow, sometimes outshining the entire galaxy that hosts it. Yet even these dramatic feeding events represent only brief moments of activity in lives that span billions of years. The black hole at the center of our own galaxy, known as Sagittarius A star, exemplifies this peaceful existence. Weighing about 4 million times as much as our Sun, it sits quietly in the galactic core, occasionally flickering with mild activity as small amounts of material wander too close. Most of the time, however, it remains nearly invisible, detectable only through its gravitational influence on nearby stars that orbit it at tremendous speeds. These sleeping giants play crucial roles in galaxy formation and evolution, their gravity helping to regulate star formation and shape the distribution of matter across cosmic scales. They're like the quiet custodians of galactic neighborhoods, maintaining order through their gravitational influence while rarely calling attention to themselves through dramatic displays of activity. Meteor showers occur when Earth passes through streams of debris left behind by comets on their journeys around the Sun. These cosmic breadcrumbs, most no larger than grains of sand, have been drifting along comet orbits for thousands of years, spread out in thin trails that can stretch for millions of miles through space. When our planet's orbit intersects these debris streams, we experience the gentle fireworks displays we call meteor showers. The Perseid meteor shower in August comes from debris left by Comet Swift-Tuttle, while the Geminids in December originate from an asteroid called 3200 Phaethon. Each year, Earth encounters these same debris streams at predictable times, creating annual celestial celebrations that have been observed and anticipated by astronomers for centuries. The meteors appear to radiate from specific constellations, giving each shower its distinctive name and character. What we see as shooting stars are actually tiny particles burning up in Earth's atmosphere, typically at altitudes of 50 to 80 miles above the ground. These cosmic visitors strike our atmosphere at speeds of up to 160,000 miles per hour, their kinetic energy converted to heat and light in brilliant but brief displays that last only a few seconds. Most are completely vaporized before reaching the ground, leaving nothing behind but their momentary trails of light across the night sky. The beauty of meteor showers lies in their predictable unpredictability. While astronomers can forecast when Earth will pass through debris streams, the exact timing and brightness of individual meteors remains delightfully random. Some showers produce steady drizzles of faint meteors, while others can create spectacular displays with dozens of bright fireballs streaking across the sky each hour. Each one a tiny messenger from the outer solar system completing its final journey in a blaze of atmospheric glory. The International Space Station orbits Earth every 90 minutes. Traveling at over 17,000 miles per hour, yet appearing to drift slowly across the night sky like a bright, steadily moving star. This orbital velocity seems impossibly fast, yet it's precisely the speed needed to maintain a stable orbit at an altitude of roughly 250 miles above Earth's surface. At this height, the station experiences about 90% of Earth's surface gravity, meaning astronauts aboard aren't truly weightless, but rather in a constant state of free fall around our planet. From the perspective of someone on the ground, the station's passage creates a peaceful spectacle. It typically takes about 4 to 6 minutes to cross from one horizon to the other, bright enough to be easily visible to the naked eye even from light-polluted cities. Unlike airplanes with their blinking lights, the space station maintains a steady glow, reflecting sunlight from its large solar arrays as it glides silently through the upper atmosphere. The station's orbit gradually decays due to atmospheric drag, requiring periodic boosts from visiting spacecraft to maintain its altitude. Without these adjustments, it would slowly spiral back to Earth over the course of several years, its orbital energy gradually dissipated by the thin wisps of atmosphere that exist even at its lofty altitude. This constant, gentle tug of atmospheric resistance serves as a reminder that even in the near vacuum of low Earth orbit, our planet's influence extends far beyond its visible surface. Astronauts aboard the station witness 16 sunrises and sunsets each day as they circle the globe, experiencing the full cycle of day and night in just over an hour and a half. They watch weather systems develop and move across continents, see the aurora dancing below them rather than above, and observe the thin blue line of Earth's atmosphere that protects all life on our planet. Their unique perspective offers a constant reminder of Earth's beauty and fragility, suspended in the cosmic darkness like a precious blue marble. Binary star systems sometimes eclipse each other with clockwork precision, creating natural lighthouses that pulse with mathematical regularity across the galaxy. These eclipsing binaries consist of two stars orbiting so close together that from Earth's perspective, one periodically passes in front of the other, temporarily blocking its light and causing the combined brightness to dim in a predictable pattern. Some of these cosmic timepieces complete their cycles in hours, while others take years to go through a single eclipse sequence. The precision of these stellar eclipses rivals the best mechanical clocks ever built. Astronomers can predict when eclipses will occur centuries into the future, and the timing remains accurate to within seconds across decades of observation. This reliability has made eclipsing binaries valuable tools for measuring stellar properties and testing our understanding of stellar evolution, as the regular dimming provides detailed information about the sizes, temperatures, and masses of both stars in the system. Algol, known to ancient astronomers as the demon star, was one of the first eclipsing binaries to be recognized and studied. Located in the constellation Perseus, it dims noticeably every 2 days, 20 hours, and 49 minutes, when its dimmer companion passes in front of the brighter primary star. This regular variation puzzled ancient observers who couldn't explain why a star would regularly grow dim and bright again with such precise timing. Modern observations reveal that many eclipsing binaries are far more complex than simple two-star systems. Some contain 3, 4, or even more stars, all locked in intricate gravitational dances that create elaborate patterns of brightness variation. These multiple systems can produce eclipse sequences that take years to repeat, with different combinations of stars passing in front of each other in a celestial choreography of extraordinary complexity and beauty. Brown dwarfs exist in the twilight zone between planets and stars, too massive to be considered planets, but too small to sustain nuclear fusion like true stars. These failed stars glow dimly with leftover heat from their formation, gradually cooling over billions of years like cosmic embers slowly fading in the darkness. They represent a fascinating intermediate class of objects that challenges our traditional categories of celestial bodies. With masses ranging from about 13 to 80 times that of Jupiter, brown dwarfs occupy a unique niche in the cosmic ecosystem. The smallest ones are barely distinguishable from large planets, while the most massive approach the threshold where nuclear fusion could ignite, transforming them into true red dwarf stars. They exist in a state of arrested development, forever poised on the edge of stellar ignition, but never quite achieving the conditions necessary to become full-fledged stars. These dim objects are surprisingly common throughout the galaxy, though their faintness makes them difficult to detect and study. Astronomers estimate that brown dwarfs may outnumber ordinary stars, making them perhaps the most abundant type of star in the Milky Way. They drift through space like cosmic ghosts, detectable primarily through infrared radiation from their slowly cooling surfaces, invisible to optical telescopes, but glowing softly in the heat-sensitive instruments that reveal their hidden presence. Some brown dwarfs have planetary systems of their own, with small worlds orbiting these failed stars in miniature solar systems that receive only the faintest warmth from their dim central bodies. These systems represent alternative pathways for planetary formation, showing that worlds can form around objects that never achieved full stellar status, creating exotic environments where planets orbit objects that are themselves more like giant planets than traditional stars. The Voyager spacecraft continue their journey into interstellar space, carrying golden records with sounds and images from Earth as they drift toward the stars. Launched in 1977, these robotic ambassadors have already traveled farther from home than any human-made objects, crossing the boundary where the sun's influence gives way to the vast emptiness between stars. Their journey represents humanity's first tentative steps into the galaxy beyond our solar system's protective embrace. Voyager 1, now more than 14 billion miles from Earth, sends back data about conditions in interstellar space, revealing a region filled with cosmic rays and magnetic fields that differ significantly from the solar, wind-dominated environment within our solar system. The spacecraft's instruments continue to function despite decades of travel through the harsh radiation environment of space, testament to the engineering excellence that created these remarkable machines. The famous golden records attached to each Voyager contain a carefully curated collection of sounds, music, and images intended to represent human civilization to any intelligent beings who might eventually encounter them. Included are greetings in dozens of languages, sounds of Earth from whale songs to human laughter, and musical selections ranging from Bach to traditional folk songs from around the world. The records also contain scientific information about our location in the galaxy and the basic properties of hydrogen, the universe's most common element. These spacecraft will continue their journey for millions of years, gradually slowing as they encounter the thin gas and dust of interstellar space, but never stopping completely. In the far future, long after Earth and the Sun have ceased to exist, the Voyagers will still be wandering among the stars, carrying their golden messages through a galaxy that will have changed beyond recognition. They represent time capsules of human achievement, preserved in the vacuum of space and destined to outlast the civilization that created them. Ocean worlds hidden beneath icy shells may be among the most common habitable environments in our solar system. Europa, Enceladus, Titan, and several other moons maintain liquid water oceans beneath their frozen surfaces, kept warm by tidal heating from their parent planet's gravitational pull. These subsurface seas may contain more water than all of Earth's oceans combined, creating vast aquatic realms that exist in permanent darkness, isolated from space by miles of ice. The discovery of these hidden oceans has revolutionized our understanding of where life might exist in the solar system and beyond. Unlike Earth's surface oceans, which depend on sunlight and a protective atmosphere, these subsurface seas derive their energy from geological processes. Hydrothermal vents on their seafloors might provide the chemical energy needed to support ecosystems, similar to the deep sea communities that thrive around volcanic vents in Earth's oceans. Enceladus offers the most direct glimpse into one of these hidden worlds through the water geysers that erupt from its south polar region. These spectacular plumes shoot hundreds of miles into space, carrying with them samples of the moon's subsurface ocean that spacecraft can analyze as they fly through the spray. The water contains salts, organic compounds, and other materials that suggest complex chemistry occurring in the dark depths below. The ice shells covering these oceans may be dynamic systems in their own right, with convection currents carrying material between the surface and the underlying sea. On Europa, the surface shows evidence of recent geological activity with linear features and chaotic terrain that suggests the ice shell is constantly being renewed and reshaped by processes occurring far below. These active surfaces create the possibility that materials from the subsurface ocean occasionally reach the surface, where future missions might sample them directly. The zodiacal light creates a faint pyramid of illumination that stretches upward from the horizon, just after sunset or before sunrise, visible only from locations with exceptionally dark skies. This ethereal glow comes from sunlight reflecting off countless tiny dust particles that orbit the sun in the same plane as the planets, creating a thin disk of material that extends throughout the inner solar system. The light is so faint that it's easily overwhelmed by moonlight or light pollution, making it invisible to most modern observers. This cosmic dust originates primarily from comets that have shed material during their passages through the inner solar system, along with contributions from asteroid collisions and the gradual erosion of small solar system bodies. Over millions of years, these particles spread throughout the solar system, creating a tenuous cloud that's densest near the sun and gradually thins with distance. The dust particles are incredibly small, typically less than 1,000th of an inch across, yet collectively they create enough scattered light to be visible from Earth. Ancient astronomers were well familiar with the zodiacal light, sometimes calling it the false dawn because of its appearance before sunrise. In locations with pristine dark skies, particularly at certain times of year when the ecliptic makes its steepest angle with the horizon, the zodiacal light can be bright enough to cast faint shadows and illuminate the landscape with its ghostly radiance. The phenomenon serves as a reminder that our solar system is filled with material invisible to casual observation. Between the planets lies not empty space, but a complex environment of dust, gas, magnetic fields, and charged particles, all interacting in subtle ways that occasionally reveal themselves through phenomena like the zodiacal light. It's a gentle manifestation of the vast, hidden architecture that connects all the worlds in our cosmic neighborhood. Pulsars are cosmic metronomes that emit beams of radiation with precision that rivals atomic clocks. These rapidly spinning neutron stars sweep their radiation beams across space like lighthouses, creating pulses that arrive at Earth with remarkable regularity. Some pulsars rotate hundreds of times per second, generating pulse trains so stable that astronomers use them as natural laboratories for testing fundamental physics, and even as navigation aids for future interstellar missions. The discovery of pulsars in 1967 initially puzzled astronomers, who briefly considered whether these incredibly regular signals might be artificial beacons created by intelligent civilizations. The signals were so precise and unlike anything previously observed that they were initially designated LGM1, standing for Little Green Men. Only when additional pulsars were found scattered across the sky did it become clear that these were natural phenomena, the remnants of massive stars that had collapsed into ultra-dense neutron stars. A pulsar's beam originates from its magnetic poles, which may not align with its rotation axis, causing the beam to sweep across space as the star spins. The radiation includes radio waves, visible light, X-rays, and gamma rays, creating a broad spectrum of emissions that can be detected by different types of telescopes. The beams themselves are incredibly narrow, and Earth happens to lie in the path of only a small fraction of the pulsars that exist throughout the galaxy. The stability of pulsar timing has enabled remarkable scientific discoveries, including the first detection of gravitational waves through their subtle effects on pulse arrival times. Some pulsars are so regular that they lose less than a second over millions of years, making them among the most precise natural timekeepers in the universe. Their clockwork precision emerges from the extreme conditions within neutron stars, where matter exists in states impossible to recreate on Earth, yet somehow produces the most reliable rhythms found anywhere in nature. Exoplanets now number in the thousands, with new worlds discovered regularly orbiting stars throughout our local region of the galaxy. These alien planets come in varieties that don't exist in our solar system, from super-Earths with masses several times our planets to hot Jupiters that orbit their stars in just a few days. Each discovery adds to our understanding of how planetary systems form and evolve, revealing that our solar system may be just one example among countless variations on the theme of worlds orbiting stars. Some exoplanets orbit in the habitable zones around their stars, regions where temperatures might allow liquid water to exist on planetary surfaces. Others follow eccentric orbits that carry them from freezing outer regions to scorching inner zones during each revolution. Still others orbit binary star systems, experiencing the light of two suns and complex seasonal patterns that would create alien environments beyond our current ability to imagine. The methods used to detect these distant worlds often rely on incredibly subtle effects. The transit method watches for tiny dips in starlight when planets pass in front of their host stars, while the radial velocity technique detects the tiny wobbles that planets induce in their stars through gravitational influence. Both methods require extraordinary precision to detect effects that amount to fractions of a percent change in stellar brightness or velocities measured in meters per second. Each confirmed exoplanet represents a world with its own unique history, geology, and potential for harboring life. Some may have experienced different evolutionary pathways that led to dramatically different outcomes from Earth's story. Others might host conditions we've never considered, with atmospheric compositions, surface environments, and energy sources that challenge our assumptions about what makes a world habitable. In this growing census of alien worlds lies the promise of eventually answering one of humanity's oldest questions about whether we are alone in the universe. The Milky Way galaxy rotates with such graceful slowness that our entire civilization has experienced only a tiny fraction of one galactic year. Since the first humans looked up at the stars, our solar system has moved less than 1% of the way around the galaxy's center. The ancient Egyptians who built the pyramids, the Greeks who mapped constellations, and modern astronomers using space telescopes have all gazed upward from essentially the same galactic neighborhood, witnessing the same stellar patterns from virtually identical cosmic coordinates. This galactic rotation creates a sense of stability that's both comforting and profound. The stars maintain their familiar arrangements not because they're fixed in place, but because we're all moving together through space like passengers on an enormous, slowly turning carousel. The Big Dipper, Orion, and the Southern Cross have looked essentially the same throughout human history, their shapes preserved by our shared journey around the galaxy's heart. Yet this apparent permanence is itself temporary. Over hundreds of thousands of years, the proper motions of individual stars will gradually reshape the constellations we know today. The bright stars that form Orion's distinctive pattern are moving in slightly different directions at slightly different speeds, and eventually their arrangement will shift beyond recognition. Future civilizations will look up at completely different star patterns, creating new myths and legends based on shapes we cannot imagine. The galaxy's rotation also means that different parts of the Milky Way experience different cosmic seasons. As our solar system orbits the galactic center, we periodically pass through the galaxy's spiral arms, regions of higher stellar density where star formation is more active. These passages, occurring roughly every 100 million years, may influence conditions on Earth through increased cosmic radiation or gravitational perturbations that affect the orbits of comets in the outer solar system. Tidal forces shape the universe on scales both intimate and vast. The same gravitational interactions that create Earth's ocean tides also sculpt galaxies, stretch comets apart, and gradually slow planetary rotations. These forces work with infinite patience, creating changes so gradual that they're invisible within human timescales, yet profound enough to reshape entire worlds over geological epochs. On Jupiter's moon, Io, tidal heating from the giant planet's gravity creates the most volcanically active world in our solar system. The moon's slightly elliptical orbit causes Jupiter's gravitational pull to vary rhythmically, flexing Io's interior and generating the heat that powers hundreds of active volcanoes. This cosmic kneading has been going on for billions of years, turning what might have been a cold, dead world into a landscape of sulfur geysers and molten rock fountains that paint the surface in brilliant yellows and oranges. Saturn's moon, Enceladus, experiences similar tidal heating, though on a smaller scale. The energy generated by Saturn's gravitational massage keeps a subsurface ocean liquid beneath the moon's icy crust, creating one of the most promising locations in our solar system for finding life. The tiger stripes near Enceladus's south pole mark regions, where this internal heat creates geysers that spray ocean water into space, visible proof of the dynamic forces at work deep below the frozen surface. Even Earth experiences tidal effects beyond the familiar rise and fall of the seas. The solid planet itself flexes slightly under the moon's gravitational influence, rising and falling by several inches twice each day in a phenomenon called Earth tide. This subtle breathing of the planet affects everything from the timing of earthquakes to the precision of atomic clocks, reminding us that even seemingly solid ground participates in the cosmic dance of gravitational forces. The solar wind carries the sun's influence far beyond the orbit of Pluto, creating a vast bubble of charged particles that defines the boundary of our solar system. This stream of protons and electrons flows outward from the Sun at speeds of several hundred miles per second, carrying magnetic fields and solar material into the depths of interstellar space. Where this solar wind meets the interstellar medium, it creates the heliopause, a boundary region where our star's dominion gradually gives way to the galaxy's broader environment. This invisible solar influence manifests in subtle ways throughout the solar system. Comet tails always point away from the Sun, not because of solar heat, but because the solar wind pushes charged particles in the comet's atmosphere outward, creating the ethereal streamers that make these visitors so beautiful. The same solar wind interacts with planetary magnetic fields to create auroras, painting the night skies of Earth, Jupiter, Saturn, and other worlds with curtains of colored light. The solar wind also carves out cavities around planets with strong magnetic fields, creating protective bubbles called magnetospheres. Earth's magnetosphere deflects most solar wind particles, channeling them around our planet and protecting the atmosphere from being gradually stripped away. Mars, lacking a strong global magnetic field, has lost much of its original atmosphere to this solar erosion over billions of years, transforming from a world that might once have supported surface water into the dry, thin-atmosphered planet we see today. During periods of high solar activity, the solar wind intensifies, sometimes overwhelming planetary magnetic defenses and causing geomagnetic storms that can disrupt satellite communications and create auroras visible at unusually low latitudes. These space weather events remind us that our seemingly peaceful solar system is actually permeated by invisible currents and fields that connect all worlds in a dynamic, ever-changing web of electromagnetic influence. White dwarf stars represent the peaceful final fate awaiting our Sun and most other stars in the galaxy. These stellar remnants, roughly the size of Earth but containing the mass of an entire star, glow with stored heat that will take billions of years to dissipate completely. They're like cosmic embers, the final chapter in stellar lives that began billions of years earlier in the collapse of interstellar gas clouds and the ignition of nuclear fusion. The journey from main sequence star to white dwarf unfolds with stately dignity over cosmic timescales. As a star like our Sun exhausts the hydrogen fuel in its core, it begins fusing helium into heavier elements, causing its outer layers to expand into a red giant phase. During this period, the star becomes hundreds of times larger than its original size, its surface cooling even as its luminosity increases dramatically. Eventually, the red giant sheds its outer layers in a series of gentle stellar exhalations, creating beautiful planetary nebulae that glow with the ionized gas expelled from the dying star. What remains is the white dwarf, the exposed core of the original star, no longer generating energy through fusion, but still radiating the heat accumulated during billions of years of nuclear burning. These stellar remnants cool so slowly that the universe isn't old enough for any white dwarf to have reached absolute zero. The oldest white dwarfs, formed when the galaxy was young, still glow with surface temperatures of thousands of degrees. They serve as cosmic archaeological artifacts, carrying within their crystalline structures the chemical signatures of stellar nucleosynthesis from epochs when the universe was fundamentally different from today. Some white dwarfs exist in binary systems with normal stars, gradually accreting material from their companions through gravitational influence. When enough material accumulates on a white dwarf's surface, it can trigger a thermonuclear explosion called a nova, briefly illuminating the star system with the brightness of hundreds of thousands of suns before settling back into quiescence for decades or centuries until the cycle repeats. Gravitational lenses bend light across cosmic distances, creating natural telescopes that magnify and distort the images of distant galaxies. This effect, predicted by Einstein's theory of general relativity, occurs when massive objects like galaxy clusters warp space-time so severely that light from more distant sources follows curved paths around them. The result can be multiple images of the same background galaxy stretched into arcs or rings that reveal details impossible to observe through conventional telescopes. These cosmic mirages allow astronomers to study galaxies that formed when the universe was young, their light magnified and focused by the gravitational lenses of massive galaxy clusters lying between them and Earth. Some of the most distant galaxies ever observed owe their detectability to this natural magnification, which can increase their apparent brightness by factors of 10 or more. The warping of space-time that creates gravitational lensing affects not just light, but the flow of time itself. Clocks near massive objects run slower than those in regions of weaker gravity, an effect that becomes noticeable around extremely dense objects like neutron stars and black holes. Near the event horizon of a black hole, time dilation becomes so extreme that processes would appear almost frozen to distant observers, while someone falling toward the black hole would experience time flowing normally from their own perspective. This gravitational manipulation of space and time reveals the fundamental interconnectedness of the universe. Matter tells space-time how to curve, and curved space-time tells matter how to move, creating a dynamic relationship that governs everything from planetary orbits to the large-scale structure of the cosmos. In the gentle bending of starlight around massive galaxy clusters, we see evidence of the universe's most fundamental forces at work on the grandest possible scales. Planetary rings exist in a delicate balance between creation and destruction, maintained by the complex gravitational dance of moons and ring particles. Saturn's magnificent ring system, while the most prominent in our solar system, represents just one example of how cosmic debris can organize itself into stable, beautiful structures that persist for millions of years. The rings exist within a narrow zone where tidal forces from Saturn prevent the particles from clumping together into larger bodies, keeping them dispersed in thin, flat sheets that catch and scatter sunlight. The individual particles that make up planetary rings range from tiny grains smaller than snowflakes to house-sized chunks of ice and rock, each following its own precise orbit around the parent planet. Shepherd moons, small satellites that orbit near the ring edges, use their gravity to maintain sharp boundaries and prevent the ring material from spreading outward into space. These gravitational shepherds create narrow gaps within the rings and sculpt the material into intricate patterns of waves and spokes that shift and change over time. Jupiter, Uranus, and Neptune also possess ring systems, though these are much fainter and more tenuous than Saturn's spectacular display. Jupiter's rings consist mainly of dust kicked up from its small inner moons by micrometeorite impacts, creating gossamer sheets of particles that glow faintly when backlit by the sun. Uranus's rings are narrow and dark, composed of material so carbon-rich that they reflect only a few % of the sunlight that strikes them. The temporary nature of ring systems adds poignancy to their beauty. Saturn's rings may disappear entirely within the next 100 million years as the particles gradually spiral inward and fall into the planet's atmosphere. This cosmic timeline means that we're living during a brief period in solar system history when Saturn wears its crown of ice and rock, a reminder that even the most spectacular celestial displays are fleeting when measured against the vast scales of astronomical time. The heliopause marks the boundary where our solar system meets interstellar space, a frontier crossed by only two human-made objects in all of history. Beyond this invisible boundary, the solar wind that has dominated the space environment throughout our solar system gives way to the interstellar medium, a realm filled with cosmic rays, magnetic fields, and the thin gas that drifts between the stars. The Voyager spacecraft, humanity's first emissaries to this distant frontier, have revealed that crossing the heliopause is not like passing through a wall, but rather like wading from a rushing river into a calm lake. In interstellar space, the environment changes dramatically from what we experience within the solar system's protective bubble. Cosmic rays, high-energy particles accelerated by distant supernovae and other violent cosmic events, become much more abundant without the solar wind to deflect them. The magnetic fields have different orientations and strengths, reflecting the complex dynamics of our local region of the galaxy, rather than the organized structure imposed by our sun's influence. The temperature of interstellar space hovers just a few degrees above absolute zero, yet this apparent coldness is misleading. Individual particles in the interstellar medium can have tremendous energies, moving at significant fractions of the speed of light. The temperature reflects only the average motion of the sparse material, which is so thin that a spaceship traveling through it would encounter fewer particles than exist in the best laboratory vacuum on Earth. Despite its emptiness, interstellar space plays crucial roles in galactic evolution. Shock waves from exploding stars compress the interstellar medium, triggering the collapse of gas clouds that eventually form new stars. Elements forged in stellar cores and dispersed by supernovae mix with the pristine hydrogen and helium left over from the Big Bang, gradually enriching the interstellar medium and enabling the formation of rocky planets and, eventually, life itself. Fast radio bursts flash across the cosmos with such intensity that they release more energy in milliseconds than our sun produces in days. Yet their origins remain largely mysterious. These cosmic beacons, detected by radio telescopes around the world, appear to come from distant galaxies billions of light years away, suggesting that whatever creates them must be among the most powerful phenomena in the universe. Some fast radio bursts repeat at irregular intervals, while others appear only once before vanishing forever. The brevity of these signals adds to their mystery. Lasting only thousandths of a second, they carry the signature of having traveled through the ionized gas that fills intergalactic space, allowing astronomers to use them as probes of the cosmic web's hidden structure. The way the radio waves are dispersed by this intervening material reveals information about the density and distribution of matter between galaxies, turning these enigmatic signals into tools for mapping the universe's large-scale architecture. Current from Highley theories suggest that fast radio bursts might originate from magnetized neutron stars called magnetars, whose intense magnetic fields can suddenly reconfigure themselves and release tremendous amounts of energy. Other possibilities include collisions between neutron stars, the collapse of massive stars into black holes, or even more exotic phenomena involving the interaction of cosmic strings or other speculative aspects of fundamental physics. Each detected fast radio burst represents a cosmic shout across billions of years and billions of light years, a brief announcement of some catastrophic or extraordinary event in a distant galaxy. These signals carry information about conditions in the early universe, the evolution of galaxies, and the behavior of matter under the most extreme conditions imaginable, all compressed into radio pulses so brief they challenge our ability to study them before they fade back into the cosmic background noise. Variable stars pulse with rhythms that have been changing slowly over centuries of observation. These stellar metronomes expand and contract in regular cycles, their surfaces heating and cooling as internal pressure waves propagate outward from their cores. Cepheid variables, among the most important of these pulsating stars, have served as cosmic distance markers for over a century, their intrinsic brightness directly related to their pulsation periods in a relationship so reliable that astronomers call them standard candles. The pulsation of these stars results from a delicate balance between gravity trying to compress them and radiation pressure trying to expand them. As a variable star contracts, its surface heats up and brightens, but this increased radiation pressure eventually halts the contraction and begins pushing the outer layers outward again. As the star expands, its surface cools and dims, reducing the radiation pressure until gravity can once again begin pulling the outer layers inward, completing the cycle. Different types of variable stars pulsate on different time scales, from RR Lyrae stars that complete their cycles in less than a day, to long-period variables that take months or even years to go through their brightness changes. Some variables are so regular that their periods remain constant to within seconds over many years of observation, while others show gradual changes in their pulsation patterns that reflect the ongoing evolution of their internal structure. The study of variable stars has revealed intimate details about stellar interiors and evolution that would otherwise remain hidden. By analyzing the precise timing and amplitude of stellar pulsations, astronomers can probe conditions deep within these stars, testing theories of stellar structure and nuclear physics under extreme conditions. These pulsating beacons serve as laboratories for fundamental physics, their rhythmic changes encoding information about the behavior of matter and energy in environments impossible to recreate on Earth. Stellar nurseries glow with the soft light of creation, regions where new stars are slowly condensing from vast clouds of gas and dust. These cosmic maternity wards can span hundreds of light years, containing enough material to birth thousands of stars over millions of years. The process unfolds with such gentle patience that entire stellar generations emerge without any sudden drama, just the gradual brightening of points of light as nuclear fusion finally ignites in their cores. Within these star-forming regions, gravity works like an invisible sculptor, slowly gathering material into increasingly dense clumps. Temperature and pressure rise gradually in these protostellar cocoons until they reach the critical threshold where hydrogen atoms begin fusing into helium, marking the moment when a cloud of gas transforms into a genuine star. This stellar birth can take millions of years from start to finish, a timeline so extended that it makes human civilization seem like a brief flicker. The most massive stars in these nurseries shine with brilliant blue-white light, living fast and burning through their nuclear fuel in just a few million years. But the smallest red dwarf stars that form alongside them will continue glowing for trillions of years, long after the universe has aged beyond recognition. These stellar siblings, born from the same cosmic material but destined for vastly different fates, begin their journeys through space together before gradually drifting apart over geological time. Young stars often retain disks of leftover material that slowly coalesce into planetary systems. These circumstellar disks can persist for millions of years, providing the raw materials for rocky planets, gas giants, asteroids, and comets. The process of planetary formation happens so gradually that by the time a star reaches maturity, its family of worlds has already settled into the orbital configurations that will persist for billions of years. The cosmic distance ladder stretches across space through a series of overlapping measurement techniques, each one calibrated against the previous rung to map the universe's vast scales. Starting with direct tax measurements of nearby stars, astronomers build outward through Cepheid variables, supernova, and other standard candles to chart distances that span billions of light years. This careful construction of cosmic measurements has revealed the universe's expansion and helped determine its age, size, and ultimate fate. Each step in this distance ladder requires extraordinary precision, as small errors in nearby measurements propagate and amplify when applied to more distant objects. The parallax method, which relies on Earth's orbital motion to create a tiny shift in stellar positions, can only measure distances to stars within a few hundred light years. Beyond that range, astronomers must rely on the intrinsic brightness of certain types of stars and galaxies, assuming that objects of the same type have similar luminosities regardless of their distance. The most distant measurements push the boundaries of observational astronomy, detecting galaxies so far away that their light has been traveling toward us for most of the universe's history. These ancient photons carry information about cosmic conditions when the universe was young, dense, and dramatically different from today. By measuring how this light has been stretched and reddened by cosmic expansion, astronomers can determine not only distances but also the rate at which space itself has been growing over billions of years. This cosmic surveying has revealed that we live in a universe that is not only expanding but accelerating in its expansion, driven by the mysterious dark energy that makes up most of reality. The precision required for these measurements pushes technology to its limits, demanding space-based telescopes and years of careful observations to detect changes in brightness that amount to fractions of a percent across cosmic time. Solar eclipses occur when the moon passes directly between Earth and the sun, creating one of nature's most spectacular and precisely predictable phenomena. The alignment must be nearly perfect for a total eclipse to occur, as the moon's shadow traces a narrow path across Earth's surface, typically less than 200 miles wide. Within this path of totality, day briefly becomes night as the moon completely covers the sun's bright disk, revealing the corona's ethereal glow and allowing observers to see stars in the middle of the day. The timing and location of solar eclipses can be calculated centuries in advance with remarkable accuracy, as the gravitational dance between Earth, moon, and sun follows precise mathematical laws. Ancient astronomers learned to predict eclipses thousands of years ago, though they often interpreted these events as omens or supernatural manifestations rather than natural phenomena. Modern eclipse predictions are so accurate that astronomers can specify the duration of totality at any location to within seconds. Total solar eclipses are relatively rare events for any given location on Earth's surface, with typical intervals of several centuries between eclipses visible from the same place. This rarity, combined with their dramatic visual impact, makes eclipses among the most sought-after astronomical events. Eclipse chasers travel around the world to experience totality, as partial eclipses, while interesting, cannot convey the profound impact of seeing the sun's corona dancing around the moon's silhouette. The brief period of totality offers unique scientific opportunities, allowing astronomers to study the sun's corona without the overwhelming brightness of the solar disk. During these precious moments, temperatures drop noticeably, animals often exhibit confused behavior, and the quality of light takes on an otherworldly character that photographs cannot fully capture. The experience connects modern observers with countless generations of humans who have witnessed these cosmic alignments with wonder and awe. Galactic cannibalism shapes the evolution of galaxy clusters through slow-motion cosmic mergers that unfold over hundreds of millions of years. Large galaxies gradually consume their smaller neighbors through gravitational interactions, stripping away stars and gas in a process so gentle that individual stellar systems rarely collide directly. Instead, the smaller galaxy structure slowly dissolves as its material is incorporated into the larger system's gravitational well. These galactic meals leave behind observable traces in the form of stellar streams, long ribbons of stars that mark the disrupted orbits of consumed satellites. The Milky Way shows evidence of having devoured numerous smaller galaxies throughout its history, with some of these ancient mergers still visible as coherent groups of stars with similar ages and chemical compositions. Current observations reveal several small galaxies in the process of being tidally disrupted by our galaxy's gravitational influence. The Sagittarius dwarf galaxy provides a dramatic example of this process in action, as it slowly spirals into the Milky Way while being stretched and torn apart by tidal forces. Its stars now form a stream that wraps around our galaxy multiple times, creating a cosmic signature of its gradual destruction. This ongoing merger will eventually distribute the Sagittarius galaxy's stars throughout the Milky Way's halo, adding to our galaxy's stellar population while erasing the smaller galaxy's individual identity. Galaxy clusters grow through similar processes on even larger scales, with massive elliptical galaxies at cluster centers continuing to accrete material from their surroundings over billions of years. These cosmic behemoths can contain trillions of stars gathered from hundreds of smaller galaxies consumed throughout their histories. The process continues today as galaxy clusters attract additional members through their immense gravitational influence, slowly building the largest gravitationally bound structures in the universe. Cosmic rays travel across the galaxy at nearly the speed of light, carrying energy from distant stellar explosions and other high-energy phenomena. These charged particles, mostly protons and heavier atomic nuclei, permeate interstellar space and constantly bombard Earth's atmosphere, creating showers of secondary particles when they collide with air molecules. Despite their name, cosmic rays are not electromagnetic radiation, but actual particles that have been accelerated to tremendous energies by magnetic fields associated with supernova, pulsars, and other violent cosmic events. The highest energy cosmic rays carry more energy than particles produced in the most powerful accelerators on Earth, yet their sources remain largely mysterious. These ultra-high energy particles are so rare that they strike any given square meter of Earth's atmosphere only once per century, making their detection and study extremely challenging. When they do arrive, they create extensive air showers that can be detected by arrays of instruments spread across thousands of square kilometers. Cosmic rays serve as messengers from distant regions of the galaxy, carrying information about conditions near neutron stars, black holes, and supernova remnants. Their magnetic charge causes them to spiral through the galaxy's magnetic field, scrambling their original directions and making it difficult to trace them back to specific sources. This cosmic pinball game means that a cosmic ray arriving at Earth today might have spent millions of years bouncing through magnetic fields before finally reaching our planet. The interaction between cosmic rays and Earth's atmosphere creates a natural background of radioactivity that has influenced the evolution of life throughout our planet's history. Some scientists speculate that cosmic ray-induced mutations may have contributed to evolutionary changes, while others study how variations in cosmic ray intensity might correlate with climate changes over geological timescales. Stellar winds sculpt the space around massive stars, creating vast bubbles of hot gas that can span dozens of light years. These stellar exhalations, driven by radiation pressure and magnetic fields, carry away significant amounts of stellar material over millions of years. The most massive stars can lose substantial fractions of their original mass through these winds, fundamentally altering their evolutionary paths and ultimate fates. Wolf-Rayet stars represent an extreme example of stellar wind activity, ejecting material at speeds of thousands of kilometers per second, while losing the equivalent of Earth's mass every few thousand years. These stellar hurricanes create spectacular nebulae around their central stars, glowing shells of ionized gas that expand outward at tremendous speeds. The material expelled by these winds enriches the surrounding interstellar medium with heavy elements forged in stellar cores, seeding future generations of star formation with the building blocks of rocky planets. The interaction between stellar winds and the surrounding interstellar medium creates complex structures called stellar wind bubbles, regions where the hot, fast-moving stellar material pushes against the cooler, denser gas of space. These cosmic bubbles can trigger star formation in their compressed boundaries, while creating low-density cavities in their interiors. Some massive stars exist within associations of similar objects, creating superbubbles where multiple stellar winds combine to excavate enormous cavities in the interstellar medium. Our own sun produces a relatively gentle stellar wind that extends throughout the solar system, creating the heliosphere that protects us from some galactic cosmic rays. This solar wind varies with our star's 11-year activity cycle, sometimes intensifying enough to overwhelm planetary magnetic fields and create geomagnetic storms that can affect satellite communications and power grids on Earth. The interstellar medium exists in multiple phases, from cold molecular clouds to hot ionized regions, each playing different roles in galactic ecology. Cold molecular clouds, with temperatures just a few degrees above absolute zero, serve as stellar nurseries where new stars condense from the cosmic gas and dust. These dense regions can persist for millions of years, slowly contracting under their own gravity until star formation begins. Warm, ionized medium fills much of the galaxy's disk, heated by ultraviolet radiation from massive stars and maintained at temperatures of several thousand degrees. This phase of the interstellar medium serves as a reservoir of material that can cool and condense into molecular clouds or be heated further by stellar explosions and stellar winds. The complex interactions between different phases create a dynamic ecosystem where matter constantly cycles between different states and temperatures. Hot ionized medium, heated to millions of degrees by supernova explosions and stellar winds, occupies large volumes of space but contains relatively little material. These tenuous regions, sometimes called superbubbles, can extend for hundreds of light years and persist for millions of years after the explosive events that created them. Despite their low density, these hot regions play important roles in distributing heavy elements throughout the galaxy and triggering star formation through their expansion and eventual cooling. The transitions between different phases of the interstellar medium create interfaces where complex chemistry and physics occur. Shock fronts from stellar explosions compress and heat the gas, while cooling regions allow atoms to combine into molecules. These boundary zones often glow with emission lines from various atoms and molecules, creating the colorful nebulae that mark sites of ongoing stellar birth and death throughout the galaxy. Gravitational waves ripple through space-time at the speed of light, carrying information about some of the universe's most violent events across billions of years. These distortions in the fabric of space and time itself are so subtle that they require extraordinarily sensitive instruments to detect, stretching and compressing distances by amounts smaller than 1,000th the width of a proton. Yet despite their infinitesimal effects, gravitational waves have opened an entirely new window for observing the cosmos. The first direct detection of gravitational waves in 2015 confirmed Einstein's century-old prediction and revealed the collision of two black holes more than 1 billion light-years away. The signal lasted only fractions of a second, but it contained detailed information about the masses, spins, and final merger of these cosmic giants. The waves had been traveling through space since long before Earth formed, carrying their message across cosmic distances until sensitive laser interferometers finally heard their whispered story. Since that first detection, gravitational wave observatories have recorded dozens of black hole mergers, neutron star collisions, and other exotic events that would be invisible to conventional telescopes. Each detection provides unique insights into extreme physics, testing our understanding of gravity, space-time, and the behavior of matter under conditions impossible to recreate in laboratories. The future promises even more sensitive gravitational wave detectors that could observe these cosmic ripples from the early universe, potentially revealing information about the first moments after the Big Bang. Space-based gravitational wave observatories might detect the slow spirals of massive black holes, tracking their orbital decay over years or decades as they gradually spiral toward merger. Dark matter comprises most of the universe's mass, yet it interacts so weakly with ordinary matter that it passes through planets, stars, and even our bodies without leaving a trace. This invisible scaffolding shapes the large-scale structure of the cosmos, providing the gravitational foundation upon which galaxies and galaxy clusters form. Despite making up roughly 5 times more mass than ordinary matter, dark matter reveals itself only through its gravitational effects. Computer simulations show that without dark matter, the universe would look completely different, with galaxies unable to form in the time since the Big Bang. The cosmic web of filaments and voids that characterizes the universe's largest structures depends on dark matter's gravitational influence to grow from tiny initial fluctuations into the complex architecture we observe today. Astronomers map dark matter's distribution through gravitational lensing, observing how its gravity bends light from distant galaxies. These cosmic mirages reveal dark matter concentrations that don't always coincide with visible matter, providing clues about how galaxy clusters formed and evolved. Some galaxy clusters show evidence of dark matter and ordinary matter being separated during high-speed collisions, supporting the idea that dark matter interacts only gravitationally. Despite decades of searching, the fundamental nature of dark matter remains unknown. It might consist of exotic particles that rarely interact with ordinary matter, or it could point to modifications in our understanding of gravity itself. Underground laboratories shield sensitive detectors from cosmic rays while waiting for the rare collision between a dark matter particle and ordinary matter, hoping to finally unmask this cosmic mystery. Planetary atmospheres tell stories of their world's histories through their chemical compositions and physical properties. Venus's thick atmosphere of carbon dioxide creates a runaway greenhouse effect that maintains surface temperatures hot enough to melt lead, while Mars's thin atmosphere provides little protection from space radiation or temperature extremes. These atmospheric differences reflect different evolutionary paths that began with similar initial conditions billions of years ago. Earth's atmosphere has been continuously modified by life processes for over 3 billion years, with oxygen levels rising dramatically after photosynthetic organisms began converting carbon dioxide and water into organic compounds. This atmospheric evolution continues today as human activities alter the composition of the air through fossil fuel burning and industrial processes, creating changes that may rival those caused by major geological events in the past. The giant planets possess atmospheres of hydrogen and helium that may extend all the way to their cores, creating environments where the distinction between atmosphere and solid surface disappears under extreme pressure. Jupiter's Great Red Spot has been raging for centuries in this thick atmosphere, powered by heat from the planet's interior and maintained by complex dynamics that we're still learning to understand. Exoplanet atmospheres provide laboratories for studying atmospheric physics under conditions that don't exist in our solar system. Some alien worlds have atmospheres of vaporized rock, while others may rain liquid methane or have clouds made of molten iron droplets. These exotic atmospheric compositions challenge our understanding of chemistry and physics, while offering glimpses of the incredible diversity of planetary environments that exist throughout the galaxy. Stellar evolution proceeds along predictable paths determined primarily by a star's initial mass, yet the details in this process continue to reveal surprises. Low-mass stars burn their fuel so slowly that they can maintain steady nuclear fusion for trillions of years, while the most massive stars exhaust their nuclear fuel in just a few million years before ending their lives in spectacular supernova explosions. The transition from main sequence star to red giant occurs when a star exhausts the hydrogen in its core and begins fusing helium into heavier elements. This process causes the star's outer layers to expand dramatically, sometimes engulfing any nearby planets while the core contracts and heats up. Our own sun will undergo this transformation in about 5 billion years, expanding to roughly Earth's orbital distance before shedding its outer layers and settling into retirement as a white dwarf. Binary star systems can follow more complex evolutionary paths deaths, as material transferred between stellar companions can alter their normal development. Some binary systems undergo episodes of mass transfer that rejuvenate aging stars, while others experience explosive events when white dwarf stars accrete enough material to trigger thermonuclear explosions on their surfaces. The most massive stars face different fates entirely as their cores become hot and dense enough to fuse elements all the way up to iron. When fusion can no longer provide enough energy to support the star against its own gravity, the core collapses in less than a second, creating the conditions for a supernova explosion that can briefly outshine an entire galaxy, while forging and dispersing the heavy elements necessary for rocky planets and life. The magnetic fields of planets create invisible shields that protect their atmospheres from the relentless solar wind. Earth's magnetic field, generated by the motion of molten iron in our planet's core, extends tens of thousands of miles into space, deflecting charged particles that would otherwise strip away our atmosphere over geological time. This protective magnetosphere has been essential for maintaining the conditions that allow life to flourish on our world. Mars tells a different story, having lost its global magnetic field billions of years ago when its core cooled and solidified. Without this protection, the solar wind has gradually eroded the Martian atmosphere, transforming what may once have been a warmer, wetter world into the cold, dry planet we observe today. Spacecraft orbiting Mars can directly measure this ongoing atmospheric escape, watching as molecules of oxygen and hydrogen stream away into space. Jupiter's magnetic field dwarfs Earth's in both size and strength, creating a magnetosphere so vast that it could contain the Sun itself. This magnetic cocoon traps charged particles from the solar wind and Jupiter's volcanic moon, Io, creating radiation belts so intense they would be lethal to unprotected spacecraft. The interaction between Jupiter's magnetic field and its moons creates radio emissions that can be detected on Earth, a kind of electromagnetic music generated by the complex dynamics of this magnetic system. Even some moons possess magnetic fields of their own. Ganymede, Jupiter's largest moon, generates a modest magnetic field that creates its own small magnetosphere, nested within Jupiter's much larger one. This discovery suggests that Ganymede may harbor a subsurface ocean of liquid water, as the magnetic field likely arises from the motion of electrically conductive salt water deep beneath the moon's icy crust. Gamma-ray bursts represent the most energetic explosions in the universe since the Big Bang, releasing more energy in seconds than our sun will produce over its entire 10 billion year lifetime. These cosmic beacons shine across billions of light years, briefly outshining entire galaxies before fading back into obscurity. Most gamma-ray bursts appear to originate from the collapse of massive stars or the merger of neutron stars, events so violent they can be detected from the edge of the observable universe. The jets of energy from gamma-ray bursts are highly directional, like cosmic searchlights sweeping across space. We only detect those bursts whose jets happen to point toward Earth, suggesting that many more occur throughout the universe without our knowledge. If a gamma-ray burst occurred within our own galaxy and its jet pointed toward Earth, the intense radiation could potentially damage our planet's ozone layer, affecting life on a global scale. The study of gamma-ray bursts has revealed that these explosions occur in star-forming galaxies throughout cosmic time, serving as beacons that illuminate the early universe when it was young and actively creating new stars. The afterglow of a gamma-ray burst can remain visible for weeks or months across multiple wavelengths, allowing astronomers to study the explosion's aftermath and learn about the extreme physics involved in these cosmic catastrophes. Some gamma-ray bursts appear to repeat, challenging our understanding of what could power such energetic events multiple times. These repeating bursts may originate from highly magnetized neutron stars called magnetars, whose intense magnetic fields can suddenly reconfigure and release tremendous amounts of energy in brief, brilliant flashes that carry across intergalactic distances. Asteroid families drift through the solar system as scattered remnants of ancient collisions, their similar orbits and compositions revealing their common origins. When large asteroids collide and shatter, the fragments retain enough of their original orbital characteristics to remain clustered together in space, creating these extended families of related objects that share the same cosmic ancestry. The Vesta family contains thousands of asteroids that originated from impacts on the large asteroid Vesta, whose southern hemisphere shows a massive crater from an ancient collision. This impact ejected so much material that fragments of Vesta occasionally fall to Earth as meteorites, allowing scientists to study samples of this distant world in terrestrial laboratories. The Dawn spacecraft's visit to Vesta confirmed the connection between the asteroid family and their parent body. Other asteroid families tell stories of destruction and dispersal spanning millions of years. The Flora family may be the source of many ordinary chondrite meteorites that reach Earth, while the Coronis family appears to be relatively young in astronomical terms, perhaps formed by a collision that occurred only a few million years ago. Each family represents a moment of cosmic violence preserved in the orbital mechanics of its scattered offspring. These asteroid families serve as natural laboratories for studying collision dynamics and the internal structure of small solar system bodies. By analyzing the distribution of fragment sizes and their orbital characteristics, scientists can work backward to understand the original impact that created each family, revealing details about the strength and composition of asteroids that would otherwise remain hidden. The heliosheath marks the region where the solar wind begins to slow and pile up against the pressure of interstellar space, creating a turbulent boundary zone unlike anywhere else in the solar system. Here, the ordered flow of particles from the Sun meets the chaotic environment of the galaxy, creating shock waves and magnetic field reversals that spacecraft have only recently begun to explore. The Voyager probes have provided our first direct measurements of this distant frontier, revealing a region far more complex and dynamic than scientists had anticipated. Temperature and particle densities fluctuate dramatically as the solar wind struggles against the interstellar medium, creating conditions that change over years and decades as the entire solar system moves through different regions of local interstellar space. Magnetic field lines that have maintained their solar origins for billions of miles suddenly encounter fields with different orientations and strengths, creating regions where magnetic reconnection can occur on vast scales. These cosmic magnetic storms can accelerate particles to tremendous energies, creating a population of high-energy particles unique to this boundary region between stellar and galactic domains. The structure of the heliosheath changes as the solar wind varies with the Sun's 11-year activity cycle, expanding and contracting like a cosmic lung breathing in the rhythm of our star's magnetic reversals. Future missions to this remote region may reveal how other stellar systems interact with their local interstellar environments, providing insights into the complex ecology of space between the stars. Trojan asteroids share Jupiter's orbit around the Sun, trapped in gravitational sweet spots where the combined influence of the Sun and Jupiter creates stable islands of orbital stability. These cosmic companions follow the same path as Jupiter but remain roughly 60 degrees ahead or behind the giant planet, locked in a gravitational dance that has persisted for billions of years. The leading group of Trojan asteroids occupies Jupiter's L4 Lagrange point, while the trailing group clusters around the L5 point, both regions where gravitational forces balance perfectly to create natural parking spaces for small solar system bodies. Thousands of these objects have been discovered, ranging from tiny rocks to substantial asteroids hundreds of kilometers across, all sharing Jupiter's 12-year journey around the Sun. Other planets also have Trojan companions, though in smaller numbers. Neptune's Trojans follow highly inclined orbits that carry them far above and below the plane of the solar system, while Mars has a few small Trojans that may be temporary captures rather than primordial members of the Martian system. Even Earth has at least one known Trojan asteroid, a small object that shares our planet's orbit around the Sun. The study of Trojan asteroids provides insights into the early solar system's dynamical evolution, as these objects likely formed elsewhere and were captured into their current orbits during periods of planetary migration billions of years ago. Some Trojans may be pristine remnants of the original solar nebula, preserved in their stable orbits like time capsules from the epoch of planetary formation. Circumstellar disks around young stars glow with the warm infrared radiation of dust grains heated by their central stars, revealing the raw materials from which planetary systems form. These disks can persist for millions of years, gradually evolving as gravity, radiation pressure, and other forces shape their structure and composition. Observations of these stellar nurseries provide snapshots of planetary formation at different stages of development. The inner regions of circumstellar disks reach temperatures hot enough to vaporize rock, creating environments where only the most refractory materials can condense into solid particles. Farther out, where temperatures drop below the freezing point of water, ice-coated grains provide the building blocks for gas giant cores and icy moons. This temperature gradient helps explain why rocky planets form closer to stars, while gas giants typically orbit at greater distances. Gaps and rings within circumstellar disks may mark the locations where planets are actively forming, their gravity carving channels through the disk material as they sweep up debris in their orbital paths. The Atacama Large Millimeter Array has revealed exquisite details of these structures, showing spiral arms, asymmetric features, and other signatures of ongoing planet formation in systems throughout our local region of the galaxy. As circumstellar disks age, they gradually dissipate through a combination of processes including photoevaporation by stellar radiation, accretion onto the central star, and incorporation into forming planets. The timescales for disk dispersal appear to correlate with the masses of the central stars, with more massive stars clearing their disks more quickly than their lower mass counterparts. Magnetospheric substorms create spectacular auroral displays when stored energy in Earth's magnetic tail suddenly releases, sending cascades of charged particles toward our planet's polar regions. These events can occur several times per day during periods of active solar wind conditions, creating dynamic light shows that can be visible across entire continents when viewed from space. The process begins when Earth's magnetic field lines are stretched and twisted by solar wind interactions, storing magnetic energy like a cosmic rubber band being pulled taut. When this stored energy suddenly releases through magnetic reconnection, It accelerates particles earthward along magnetic field lines, creating the conditions for intense auroral activity that can persist for hours. Substorms represent one of the most dynamic processes in Earth's space environment, capable of injecting enough energy into the magnetosphere to power major cities for days. The energy release occurs in a complex sequence of phases, with the explosive onset phase lasting only minutes, while the recovery phase can extend for hours as the magnetosphere gradually returns to its previous state. Understanding magnetospheric substorms has practical importance for space weather forecasting, as these events can damage satellites, disrupt radio communications, and even affect power grids on Earth's surface. The complex physics involved in substorms continues to challenge scientists as the precise trigger mechanisms remain debated despite decades of study with spacecraft and ground-based instruments. Solar prominences arch gracefully above the sun's surface, following magnetic field lines that can extend hundreds of thousands of miles into the corona. These enormous structures, made of relatively cool plasma suspended in the sun's hot outer atmosphere, can persist for days or weeks before suddenly erupting and sending material streaming into interplanetary space. The material in prominences follows the invisible architecture of magnetic fields, creating loops, sheets, and twisted ribbons that reveal the complex magnetic topology of the solar corona. When viewed from the side against the darkness of space, prominences glow with the red light of hydrogen atoms, creating some of the most beautiful images in solar astronomy. Quiescent prominences can remain stable for extended periods, their plasma trapped in magnetic bottles that prevent it from falling back to the solar surface under gravity. These structures demonstrate the sun's ability to support enormous masses of material through magnetic forces alone, creating temporary bridges between different regions of the solar atmosphere. When prominences erupt, they can launch coronal mass ejections that carry billions of tons of solar material into space at speeds of millions of miles per hour. These eruptions follow the same magnetic field lines that previously contained the prominence, but now stretched and distorted beyond their ability to maintain confinement, releasing their stored energy in spectacular displays of solar activity. Cosmic dust pervades the galaxy, forming vast clouds that can obscure distant stars while serving as the raw material for future generations of stellar and planetary formation. This interstellar dust consists of tiny solid particles, typically smaller than cigarette smoke, composed of elements like carbon, silicon, and iron that were forged in the cores of previous generations of stars. And so our gentle journey through the cosmos comes to a quiet close. We've drifted together among the patient stars, explored the slow breathing of galaxies, and discovered that the universe's most profound mysteries unfold not in violence, but in whispers across unimaginable spans of time. Each fact we've shared tonight carries the same peaceful rhythm that governs the cosmos itself, reminding us that in a universe of gentle giants and cosmic lullabies, there's always something beautiful waiting to ease us into rest. Sleep well, knowing that above you, the stars continue their ancient dance, and the universe keeps its quiet watch over all who dream beneath its endless starlit sky.